moving on from these examples of reputation system to closer to the search engines that we've been discussing in this course. Um, I would like to lay down a general comment about a reputation system, and we're going to see how this general comment can be then used to develop some kind of an authority score for different documents on the web. So here's the idea. Your reputation is high, and this is pretty intuitive. Your reputation is high if other highly reputed individuals are recommending you. Right, and this is something intuitive. Okay, so if let's say 10 of my family members say that I'm an expert computer scientist, that doesn't mean anything, right? Because they may not be even from a CS background. But if I get the same kind of a remark from, let's say, a colleague or a superior who is himself an expert in computer science, then that carries more weight. This is the idea behind citations also. If you have citations, uh, firstly, if you get your paper published in a reputed journal, and what is a reputed journal? A reputed journal is a journal where whose papers are again cited very frequently by other reputed papers, right? So it's kind of a recursive definition, but I hope it's intuitive. So what we're going to do is we're going to use this intuition to develop some kind of an authority score or a reputation score for a document on the web. So let's say that we represent the web by a graph. Okay, so a graph is a set of nodes called vertices and a set of edges between those vertices. And in this case, the set of vertices is the set of all web pages. Okay, so using our previous notation, if we assume that n is the total number of documents in your web corpus, we're going to have n vertices in this graph, each vertex standing for a particular document. So each doc ID is, has a one-to-one mapping with a vertex. And if page U, okay, or if document U has a link within it to page V, then we're going to have an edge from U to V in this graph. Okay, so this is a directed graph. That means edges have directions on them. And if there is a link to V from page U, then you're going to have a directed edge from U to V. So what is an anthropomorphic interpretation of this edge? Basically, this edge is indicating that document U is positively endorsing document V. Right? Whoever has created document U, that author expects you to go and read document V. Yeah, I think your video is still stagnant, so just okay. But did you follow up to this point, or did you get disconnected before that?
So, could you please start again?
Start this again?
Yes, sir. So we didn't. The video stopped when you said anthropomorphic at that point.
Okay. So yeah, what I meant is if you think of, can you turn off the microphone? I can hear some sound there. Yeah, thank you. So what I was saying was, imagine you and we not as documents, but say as human individuals. So just as a person you may recommend another person we to someone who's talking to you. So basically you may recommend that why don't you go and speak to we. In the same way, think of a web page having a link to another web page as, so if a web page, if the document u has a link within it to document v, then what I was saying was that when a web page u has a link to another web page v inside it, it is it can be interpreted as a positive endorsement of web page v, because the author of web page u is expecting the reader to click on that particular link and go and read web page v, which is why that link is there. Otherwise, why would the author provide a link to v, right? Unless the author wants you to uh, visit v, at least in some circumstances. So that kind of positive endorsement is represented by an edge from u to v. So based on this and this intuition, I want one of you to come up with a formula for the page rank of a page u, an arbitrary page in the corpus. So I'm going to call pi of u as the page rank, or you can say the reputation of u, or you can call it v. I mean, doesn't matter whether you use u or v. Basically, I want you to come up with a simple formula based on your own intuition for the reputation or the page rank of any arbitrary vertex in this graph, assuming that the edges of this graph represent some kind of a positive endorsement of the web pages that are being linked.
The number of uh, so edges of the form v comma u, where u is the page of which the rank is to be determined,
Okay.
could give.
Yeah. So the first, the simplest possible score is the number of pages linking to you, right? The number of pages having a link within them to this page u. But actually, what we said above is not just that the number of individuals thinking highly of you should be high, should be large, but their own reputation also matters. Right? The reputation of those people who are linking to you, or those pages that are linking to you, that is also going to play a role in determining the page rank of this page. So can you think of a simple modification of this?
So like each page which is linking to it,
Mm-hmm.
like could be multiplied by a weight of some sort, like maybe the number of pages linking to it, so that
Okay, let's take a simple example. Let's say we have a page V, and let's say there are three other pages, A, B, and C, linking to V. Okay, so what would be the what would be a simple formula for the page rank of V using this intuition?
so the using the first one, it would be 3, of course, but like if we had to take the reputation of A, B, and C into consideration, we'd also need to know like how many pages are linking to A, B, and C
Oh,
themselves.
okay. So let's say that the reputation of A is the page rank of A. You can give a recursive definition. That's not a problem. Let's say you know
Okay.
what the reputations of A, B, and C are.
Okay, so then you can say just say page rank of A plus page rank of B plus page rank of C.
Okay. Yeah, this is a simple formula for computing the reputation of V. It's simply the sum of the reputations of the individual pages that are linking to V. Okay. So in general, we can say that the page rank of V will be the summation of the page the page rank or the reputation of all pages U such that U has a link to V in it. Okay, does everybody understand this notation? Page rank of V is the summation of the page ranks of all the pages U such that there is a link to V from each of these pages. Okay, that is U comma V is part of this, is an edge in this graph. Now, how many such formulas will be there? So assuming that there are n documents in your corpus, you will have n such equations, right? One for each page. So let's try to add all those equations. Okay, so there'll be some equation for the page rank of V, there'll be some other equation for the page rank of U, there'll be some other equation for the page rank of A, and so on. So there'll be n such equations, and what we want to do is, okay, so the page rank of V is the summation of all the reputations of pages that link to V. So if we add all these n equations up, on the left hand side, what will we get? We will get summation of the reputation or the page rank of every vertex V in the graph, right? And on the right hand side, we'll get, so what is this? This is the summation of all the in degrees of every node. Okay, so let me define. In a directed graph, if you've done a course in discrete math, you would have studied what the out degree and the in degree of a vertex are. The out degree of a vertex is the number of edges out of that vertex. Right? So if you have a vertex that has 4 edges out of it, then the out degree of V would be 4. And if you have a vertex that has 3 edges coming into it, then the in degree of that vertex is said to be 3. So the in degree is the number of incoming edges, and the out degree is the number of outgoing edges from that vertex. For this particular lecture, I'm going to, whenever I speak of the degree of a vertex, I'm going to be referring to the out degree. Okay. But there are two kinds of degrees, just to. So what is this? How many terms are being added here? Okay, so the number of terms here in this equation is the in degree of V. Right? Because every page that has a link to V. Will you turn off the microphone, please? I'm hearing some echo. Yeah. The number of terms that are being added in this equation is the number of web pages that are linking to V. And a link to V is represented by an edge from that particular vertex into V. So the in degree of V will be the number of pages having a link to V. So when on the right hand side here, we are going to add up the in degrees of all of these vertices. Okay, so here we are summing up the reputations of all the vertices. Here we are summing up the reputation of all the vertices that have an edge to each of these vertices. Now, is there any reason to suspect that these two are going to be the same? So basically my question is, is this system of equations, um, going to have a solution?
So, I had a question like basically if A has a link to a page B, what if B also has a link to a page A or to the page A? Then how do we resolve this situation? Because to find out the rank of A, we need the rank of B, and to find out the rank of B, we need the rank of A.
Yeah.
Then how do we do it?
Okay, so let's take an example. Let's say this is A. It has an edge to B. B has an edge back to A, and let's add another vertex C. B has an edge to C, and then C also has an edge to B. So here we would say that the page rank of A is going to be equal to the page rank of B, right? Because the incoming edge, so A's reputation depends on those pages that are linking to A, and B is the only page that's linking to A. The page rank of B is going to be the page rank of A plus the page rank of C. And the page rank of C, actually I shouldn't call it the page rank because this is actually not the right formula for the page rank. This particular formula that we saw, this is just a first attempt to come up with some kind of a reputation score. But it's not the formula that was used in the original Google paper. So uh, I'm just going to call it the reputation of uh, the vertex instead of page rank. So the reputation of C is going to be just the reputation of B. So if you take these three equations, you can see that if so, reputation of A is equal to reputation of B, reputation of B is equal to reputation of C. So all three of them are the same, and yet one of them is also the sum of the other two. That means reputation of B is twice of reputation of B. That means reputation of B is 0. Okay, so the only solution to this system of equations in general is going to be where all the reputations are 0, because otherwise it's meaning, I mean, there's no reason why the sum of the reputations on every vertex has to be equal to the sum of the reputations of all the incoming vertices into that into each of the vertices, and then adding them all together. There's no reason why the right hand side should be equal to the left hand side, which is why you get a trivial kind of a solution if you try to solve these equations where all the reputations are 0. So clearly this particular attempt at arriving at um, sort of a consistent formula for the reputation score is leading to problems. So let's try to modify the formula so that we can so that we don't get this kind of a problem where we, even if we add everything on the left hand side, let's try to come up with a formula so that the right hand side will actually add up equal to the left hand side. So how can we do that? So here's the original formula. The reputation of V is equal to the sum of the reputation of all pages that link to V. So how could you modify this formula? And one hint I could give you is, let's use the degree of uh, a particular vertex in this formula. Actually, let me give you the formula directly, and then maybe I should ask you to justify why this formula may make sense. So d sub u is the degree of u. Okay, and as I said, when I use the word degree, I'm referring mainly to the out degree of vertex u. So suppose we take the reputation of all the vertices that are linking to V, but we don't add up the reputations. We take the reputation of a particular, let's say we take the reputation of this particular vertex. Instead of just adding it, we are going to say that only a fraction of its reputation is going to contribute to the reputation of V. So if it has 3 links out of it to 3 different vertices, only 1/3 of its reputation is going to get contributed to the reputation of V. Okay, so we are dividing the reputation of this particular of each of these vertices by their respective out degrees, because this is the out degree is just the number of edges out of that vertex. Now if we I mean, this is relatively intuitive if you think about it, because if a particular page is linking to 5 other pages, that means it's recommending 5 different pages, and so its own reputation is going to contribute 1/5 to each of those 5 pages. Whereas if it was linking to exactly one page, that means it's putting all its weight behind um, one particular page, right? I mean, if you again anthropomorphize, it's like my saying that if you come and ask me who's a good candidate to be hired for this job, and I say I can only think of this particular person. So based on what my reputation is, I'm putting all my weight behind one particular person. Whereas if I say, all 3 of these candidates are good, then whatever my reputation is, it's going to sort of get divided among those 3. Okay, so it's an intuitive formula. And the reason why this makes sense is if you add up these equations for all the vertices in the graph, on the left hand side, you'll be adding up all the reputations of the vertices.
So,
Yeah.
So could we kindly take a break for 5 minutes?
Okay, let me just finish this one sentence and we'll stop for 5 or 10 minutes. So if I add up the reputations on the left hand side, I'll get sigma of the reputations of V. Whereas here, how many times will, so if I add up the right hand side, imagine n equations and we are adding up the right hand side of all those n equations. How many times will this term pi of u divided by d of u appear on the right hand side? It will appear d of u times, right? Because it will appear once for this particular, so let's say this is u, it's going to appear once in the equation for this particular vertex, once in the equation for this particular vertex, and once in the equation for this particular vertex. So effectively, by adding up, and every time this particular, any of these vertices is chosen, we are going to be adding a term pi of u divided by 3. So to this score, pi of u divided by 3 to this score, and pi of u divided by 3 to this score. So when we add up the right hand side, we are going to end up with pi of u. Right, again for all u in V. So you can see that the left hand side is equal to the right hand side, and so we get a consistent score that way. Okay, we don't have to this is a consistent formula which will ensure that the left hand side remains equal to the right hand side. Okay, we can stop here. Let's continue after the break. So just before the break, we came up with this modified formula for computing the reputation score for a web page based on the reputation scores of all the pages that are linking to this page, that are pointing to this page. So if a page A points to a page B, then A is going to contribute not its entire reputation score to B, but a fraction of its reputation score. And that fraction is going to be 1 divided by the out degree of A. Okay, the total number of edges out of A is the out degree of A, and it's going to contribute 1 by d of A to each of 1 by d of a times its own PageRank score to the PageRank score of all the vertices on the other end of those outgoing edges. And if you focus your attention on a particular vertex B, it's going
Sir,
to, yeah.
so I had a question. So like, if so once these page ranks are calculated, if a new link comes up, what will happen then, sir? Like, let's say B was not linking to A previously, and then suddenly it gets a link. Then what, sir?
Yeah, so computation of PageRank is something which we'll talk about a little later. So the brief answer is that there is a particular iteration. So these PageRanks are computed in a relatively iterative way. First of all, we have to come up with the right formula. But assuming we come up with the right formula, then you can keep on applying that formula iteratively. So if a new page comes up, you will compute its page rank from scratch, and then the pages to which it's linking, those pages will update their page rank based on this new link. And then the other pages that were being linked to by those pages are going to update their page rank. And this may have to go on for a few iterations, but the computation is going to pretty much converge it's going to converge relatively fast to a stable set of values, to some equilibrium set of values. So but that's the rough high level answer, but we'll look at
Okay,
that
sir.
in more detail later. So let's apply this to a simple graph of this kind which has just three vertices A, B and C, where these are the links. So the page rank of A would be determined only by the page rank of. So by the way, again, it's a misnomer to call it the page rank, because this is not the actual formula. Again, it would be more accurate to call this as a naive page rank. So let me call it the naive page rank, because we're going to come up with a more improved formula later. So the page rank of A, or the naive page rank of A, is going to be determined by the page rank of B, but it's not going to be equal to the page rank of B because B has two outgoing vertices. So B's reputation is going to be divided among these two vertices. So it's going to be half of that. The page rank of C is similarly going to be the page rank of B divided by 2, because this is the only incoming link into C, and the page rank of B is going to be distributed among these two. The page rank of B is going to be determined by both A and C because there are two incoming edges. Now, A has no other outgoing edge, right? So its page rank is going to contribute entirely to the page rank of B, and the same goes for C. So these are the three equations, and there are three unknowns, and if we solve for them, what would you get? So firstly, if you add up the left hand side, you will get pi of A plus pi of B plus pi of C. And if you add up the right hand side, you will get pi of A plus pi of C plus pi of B. So the left hand side and the right hand side are the same. Now if you've probably done a little bit of linear algebra, right? So if you have n equations and you have n unknowns, you should ideally be able to solve for those n unknowns. Okay, using simple, you can represent this system of linear equations by a matrix, and then take the inverse of the matrix and compute the solutions. But in this case, these three equations are not independent. Okay, because when we add up the left hand side and the right hand side, we get the same values on the left and on the right. So in some sense, there are one of these equations. So if we take pi of B is pi of A plus pi of C. So if you substitute pi of A by pi of B by 2 and pi of C by pi of B by 2, you'll get pi of B is equal to pi of B, which is trivially true. Similarly, pi of A is equal to pi. So these two need to be the same, and pi of B needs to be half of what these two are. Okay, that's as long as we are able to satisfy it. Okay, so pi of A should be equal to pi of C, and that should be half of pi of B by 2. That's what these three equations are saying. This third equation trivially follows from these two. Okay, so this is not an independent equation because it's not adding any extra constraint. Okay, it follows from these two. Okay, because pi of B here is, if you add up these two equations, you're going to get this third equation. Okay, so this is not an independent equation. This is not a system of three independent linear equations. This is a system of two independent linear equations in three unknowns. And this is what the constraints are. Now you can come up with an infinite number of values, solutions for this system. Hello, have you lost your connection again?
No, sir. We can. No,
Okay.
sir.
Okay, so the video is gone, but it's okay. If you're able to hear me, that's and see what I'm doing, that's fine. So I can, one solution is, again, all three of them could be 0. Another solution is pi of A could be 5, pi of C could be 5, pi of B could be 2.5. That will satisfy these three equations. Another solution is pi of A could be 10, pi of C could be 10, pi of B could be 5. So what we're going to do is we're going to add one more constraint. We're going to say that the sum of the page ranks of all the vertices needs to be 1. Okay. So we're going to try to come up with a scoring scheme so that if we add up the page ranks of all the nodes in the graph, that value must be 1. Now with this extra equation, and obviously we also want to be clear that we don't want negative values for any vertex. Okay, so the page rank of every vertex should be non-negative and they should all add up to 1. So a solution which has all of them equal to 0 is not a valid solution because it doesn't satisfy this particular constraint, which is going to be a common constraint for every single graph. So if the sum of the page ranks needs to be 1, then what are pi of A and pi of C going to be? Now can you solve these equations?
Pi C would be 0.25. Pi B would be 0.5.
Yeah. So the sum has to be equal to 1, and A and C are basically the same and they are half of B. So if we substitute pi of B by, so pi of A is pi of B by 2, pi of B is just pi of B, pi of C is also pi of B by 2. Sum of these three should be equal to 1. So that means twice of pi of B should be equal to 1, or pi of B should be half. Okay. So the solution pi of B is 0.5 and pi of A is 0.25, half of 0.5. Is that clear, this example? Yeah. Any questions?
So let's say
Your
case
voice is
of
a little muffled. Could you, for some reason, your voice is not clear anymore.
also.
It's still not clear.
So like
Mm-hmm.
if we let's say a good site shop which is giving out a lot of links, like but its weight is being distributed amongst all those links.
Mm-hmm.
So and then later on, so will it? I mean, I just wanted to confirm this. Like as more and more sites keep linking to that good site, its weight would also increase, right, sir?
Yeah, its weight will also increase.
Okay. Yes, sir. That's it.
Yeah. So there's another way to think about this naive PageRank score, and that way is the following. Imagine this graph, okay, the same graph with all the web pages and their links to one another. And imagine a monkey randomly starting from a vertex in the graph and then doing some kind of a random walk through the graph. So what the monkey does is when it comes across, and let's say it's at vertex u, and it sees 4 outgoing edges from u, it's going to choose each of these paths with the same probability. Okay, so with the probability of 1 by 4, it's going to follow this particular edge. With the probability of 1 by 4, it's going to follow this particular edge, and so on. So at every second, the monkey makes one hop from one vertex to the next vertex based on this kind of a scheme. It will look at all the outgoing edges from that vertex, and it will randomly choose one of those outgoing edges, and then if at t equal to 0 the monkey was at u, at t equal to 1 the monkey will be at one of these 4 vertices. Then at t equal to 2 the monkey will be, let's say at t equal to 1 it was at a, then it's going to be at one of these outgoing edges from a at the next time instant. Okay, so let me ask you this. Suppose I say t sub v is the fraction of time the randomly surfing monkey is at v. Can you write a formula for t sub v in terms of all these vertices which are pointing to v? So t sub v is the fraction, or you can think of it as the percentage of time that in the process of randomly walking through this graph, this monkey will be at vertex v. So one thing that's clear is the sum of these t sub v's is going to be 1, right? Because the monkey's time has to be divided among all of these v vertices, and clearly since we are talking about the fraction of the time that the monkey is spending on each vertex, the sum of those fractions needs to be equal to 1. But can you express t sub v in terms of the values of t for these vertices that are pointing to v?
So I wanted to clarify, sir, like 1 second is what exactly? Is it the time taken for the monkey to go from one vertex to another?
No, so imagine time to be divided into discrete units. Okay, so this is t equal to 0, 1, 2, 3, and so on. So at each time point, the monkey is making an instantaneous jump to a new vertex, and then it's staying there for 1 second, and then at the next time, at the next instant, it's jumping to a new vertex. It's staying there for 1 second. So the transition time is, let's say, 0. So it's just, the monkey is here and then suddenly it goes there, it goes like that, and so on. So what is the probability that the monkey will be at vertex v at any given time? Suppose I know the probability with which it's going to be at A. I know the probability with which it's going to be at B, C, and so on.
Sir, I think it will be the sum of these, like T of A by dA plus T of B by dB plus T of C by dC, so on up till all the vertices that are actually pointing to V.
Yeah. And why is that? Because there are, so if there are, so in this case there are 6 different vertices that are pointing to V. So there are 6 different routes by which the monkey can come to V. either the monkey was at A and followed this edge, or the monkey was at B and followed this edge, or the monkey was at C and followed this edge, and so on. What is the probability that the monkey was at A, T sub A? What is the probability that the monkey would follow this edge out of A to V? That would be 1 divided by the out degree of A, because we just said that the monkey is going to follow each of the outgoing edges with equal probability. And so if the out degree is D sub A, then the monkey is going to follow this particular edge with a probability of 1 by D sub A. So with this particular probability, so if the monkey was at A with this particular uh, with a probability of 1 by D sub A, the monkey will be at V. So if you want to calculate the probability with which the monkey will be at V, these are the 6 different mutually exclusive ways in which the monkey can land up at V. Either it was at A and then it followed this particular edge, or it was at B and then it followed this particular edge, or it was at C and it followed this particular edge, and so on. So effectively, we are saying that this is equal to T sub U divided by D sub U for all U that have a link into V. For all vertices U that have a link that are pointing to V. So you can see that it's the same formula, right? We just had pi of V being equal to the pi of U divided by D sub U. And just like this particular constraint that we imposed, we said that sigma of T sub V's should be equal to 1. Again, a very intuitive constraint. And I hope you recall that if you have a set of events that are mutually, that are disjoint, then the probability of either of them happening is the sum of the individual probabilities. So that's what we are doing here. So is that clear? How, and obviously this is also true that for all vertices V, the value of T sub V has to be non-negative. So you have the same exact system of equations for both a randomly surfing monkey and this particular reputation score that we came up with using a different kind of an intuition. So in effect, what this naive PageRank score is telling you is how likely is it that if I was randomly surfing this graph, how likely is it that I will be at a particular page V? That will be its PageRank. Okay, so if there are a large number of links pointing into a particular web page, and each of those links, each of those vertices which are have a high probability of the monkey being there, relatively high probability, then it's very likely that the monkey will be at the vertex that they are commonly pointing to. Any questions about this?
So no, sir.
No. Okay. Okay, so here's a simple example. Let's take a graph A going to B, going to C, going back to A. So what would be the page rank of A, B, and C in this graph?
So T of A would be T of C because there's only one link coming in from to A, and that is from C, and C has exactly one outgoing link, and that is to A. And similarly, I think all of them will just be equal. Equal.
The page rank of A depends on the page rank of C, and in this particular way, it's going to be equal because there's only one edge into A. Likewise, there's only one edge into C, that's from B, and there's only one edge from B, that's from A. And obviously, the sum of these three needs to be equal to 1. So what would be the solution?
So 1 by 3, 1 by 3, 1 by
Yeah.
3.
So each of them will have a page rank of 1 by 3, 1 by 3, and 1 by 3. What if this was a ring? Okay, so A1, A2, A3, A4, A5, and so on up till A sub capital N, okay, where capital N is the number of documents. What would be the page rank of uh, all these N web pages?
Yeah, so I think it would be 1 by n.
Yeah, so every web page will have the same page rank. Again, this graph is perfectly symmetric, so there's no reason why you expect the page rank of any page to be different from the page rank of any other page. But even if you write down the equations, you're going to have a series of equations of this particular form, and then they all have to add up. All the page ranks have to add up to 1, and they're all equal. So that means every individual page rank is going to be 1 by n. Now I'm going to make a small modification to this graph. Okay. Suppose you are the author of web page A2, and let's say you belong to a particular university, and the university has this sort of a naive link policy, where the first student has a link at the bottom of his page saying next, and that goes to the next student. Then from your page, you have a link at the bottom saying this is the next student in, I don't know, roll number, order, or whatever, to 3, and so on. And you sort of link back to the last page, which could be a common page for the whole class, and then that's going to point to the guy whose roll number is the first. Now suppose you and your friend, so your friend is the one who has this web page A1, and you have your home page A2. Now you decide, you both want to come up with a way by which you can improve your own respective page ranks. How would you? So imagine yourself to be A2. How would you modify the links out of your page so that your page rank can go up? So obviously you cannot manipulate the links out of other pages. You can only manipulate this particular edge. Okay, you can add more edges, or you can delete this edge and add an edge elsewhere. Or what can you do? Can you sort of collaborate with A1 to ensure that you both have a very high page rank? Initially your page rank is 1 by n, which is what everybody has, but it's a very small value. You want to improve your own page rank. How do you do that?
So if E2 links back to A1, so
Okay.
so A2's rank itself would be just the rank of A1, but A1's rank would now be like it will become AN plus half of A2.
Yeah. Firstly, let's say you delete this edge, and you now, instead of pointing to A3, you point back to A1. Okay. What will be the page rank of A3 now?
It will be 0, so
Yeah, 0, because it has no incoming edges. Right? So page rank of A3 will be 0. What will be the page rank of A4?
again 0.
Again 0, because the only incoming edge is from A3, and A3 has 0 reputation. So the reputation of A4 is going to be 0. Similarly, the reputation of all these pages is going to be 0, 0, 0, 0, 0, 0, thanks to your just changing this particular link. This is also going to be 0. What about A1? What will be the page rank of A1?
So it would have to be half, because all the other pages have to have a rank of 0, and A1 and A2 must sum to 1. So A1 and A2 would both have, I think,
Yeah.
half.
So obviously the page rank of A1 here has to be equal to the page rank of, uh, actually it will be the page rank of A2 plus the page rank of AN. Okay, but the page rank of AN is 0. We know that. So this doesn't make any difference. So these two page ranks are the same and all of them have to add up to 1. And all of them other than these two are 0. That means these two have to be equal to half. So the page rank of these two pages is equal to half. So basically what you've done is if you had 100 pages here, you have improved your page rank from 1 by 100 to half just by collaborating with one another. And you've also destroyed the reputation of all these other pages. So this is one of the problem with this naive PageRank formula. It is vulnerable to collusion. Okay, you can collude or collaborate with one another to artificially inflate your page rank at the cost of the reputation of others. Okay.
So, but in a but in this real world, so like I mean, if we have links like that, we would have a much more interconnected kind of structure. So even then, is it possible to collude with some page and increase your rank?
Um, it may be more difficult, but you could, for example, you could try to create some web pages of your own and then have links to each other, and that way you can play that kind of a role. Let me actually take a slightly different example. Let's say you have A, B, C. Okay, so this is one community of people, and you have another community of people, P, Q, and R. What is the page rank of these 6 pages? Clearly, these 3 have to be the same,
I'd say 1 by, yes, sir.
and these 3 have to be the same. Okay, and the 6 of them have to add up to 1.
So it can be anything, sir. Like I mean, in any ratio, it can be like as long as uh, pi a plus pi b plus pi c plus pi c plus pi q plus pi r are equal to 1. It
Yeah.
can be any ratio.
Yeah. For example, you can say that I'm going to make the total of the page ranks here to be 0.4, and I'm going to make the sum of here to be 0.6, so that they all add up to 1. But then each of these is going to be zero point 0.6 divided by 3, which is 0.2 each. And these 3 are going to be 0.133 each. Okay, 1/3 of 0.4. So that's one way. Or you can divide them half and half. I mean, there are an infinite number of solutions to this particular graph. Okay. So apart from vulnerability to collusion, the other problem with this naive PageRank approach is that in some graphs like the following, you can have an infinite number of solutions. You want basically one single solution, one single set of assignment of values for all the web pages, which is unique. You don't want an infinite number of solutions. Here's another problem. Let's take another example of a network: A, B, C, and then you have D. What would be the page rank of these 4 pages?
So page rank of C would be, sorry, page rank of D would be page rank of C.
Okay.
Then so page rank of C would again just be page rank of B, and page rank of A would be page rank of C divided by 2,
Okay.
and page rank of B would be page rank of A. Sorry, PageRank of D would also be PageRank of C divided by 2.
Yeah, because there are two outgoing edges from C. So C's reputation is distributed between A and D. And PageRank of B is equal to the PageRank of A. Okay. And the 4 should add up to 1. Now, A, B, and C are basically the same. So I'm just going to write these two as pi of C. What is pi of D? It's pi of C by 2. Sorry, we also have this particular equation. The page rank of A should be half of the page rank of C from this equation. And if you combine these two equations, the page rank of A must be equal to the page rank of C. Right? So how can both of these conditions be satisfied? That means page rank the page rank of C divided by 2 should be equal to the page rank of C. Right? That means the page rank of C should be 0. And if this is 0, what will be the page rank of D? That will also be 0. And what about the page rank of A? That will also be 0. The page rank of B will also be 0. But then we are not satisfying this particular equation. That the 4 are not adding up to 1. So this is an example where there is no solution. There is no feasible solution to this particular system of equations. So for this particular graph, naive PageRank is not going to give you any solution at all. For this particular graph, it gave you an infinite number of solutions. Okay, so these are two different kinds of problems with it. And moreover, we saw that it's vulnerable to something called link spam, where you can have people manipulating links on their page, and that having an impact on the page rank of other pages out there on the web. So what we're going to do now is we're going to come up with a more sophisticated, slightly more sophisticated technique, which is actually now going to be the PageRank formula that was originally used by Sergey Brin and Larry Page in their paper that was published in the late 90s. And it's just going to be slightly more complicated than this. It's just a simple extension of what we discussed so far. Imagine going back to that monkey randomly surfing the graph. Imagine this monkey so what this monkey is going to do is it's not only going to follow this particular technique that I described, where it's at one particular node at any time instant, and then at the next time instant it's going to land up in one of the outgoing one of the neighboring vertices to this particular node based on an equal sort of likelihood of walking along either of the outgoing either of these 4 outgoing edges. The monkey is going to do one additional thing. It will sometimes decide that it's not going to follow this kind of a technique. Sometimes it's going to decide I'm going to randomly jump to an arbitrary vertex in the graph. So think of how you browse the web, right? You start from a particular page, you follow a link, you would end up in some other page, you follow some links on that, you end up on some other page, and so on, until you decide that you've basically browse whatever you wanted to in that particular interconnected network of pages, and then you just go back to your at the top of your browser and say I want to go back to or I want to go to google.com, or I want to look at imdb.com or something like that. So part of the time we are following links, part of the time and after that sometimes we decide that we're not going to follow any links, we're going to go separately to some different page. So that's what the monkey is also going to do. The monkey is going to decide that with a finite probability, I'm going to jump randomly to some other vertex in the graph. And if I don't do that, then I'm going to basically continue doing whatever I was doing, looking at the outgoing edges and see uh, what the what the out degree is, and then randomly pick one of those outgoing edges and land up at the vertex on the other side. So here's a simple extension of that PageRank formula. So the PageRank of V so far was just the summation of the PageRank of all incoming vertices U divided by their out degrees for all vertices U that are pointing to V. Now what we are going to do is the monkey is going to, so with the probability of epsilon, so epsilon is what we call as the reset probability. With a probability of epsilon at each time point, the monkey is going to randomly jump to a particular, to an arbitrary vertex in the graph. That means with a probability of 1 minus epsilon, the monkey is going to continue following the scheme that it was earlier. So what is the probability that the monkey will end up in vertex V? Well, the standard way of ending up at vertex V is to be present at any of the neighbors of V and then follow the edge from U to V. Okay. But now the monkey is also going to randomly toss a coin, and with a probability, randomly with a probability of epsilon, the monkey is going to randomly jump to some vertex in the graph. So what is the probability that I'll end up with at vertex, that the monkey will end up at vertex V by randomly jumping to some node in the graph? It's going to be epsilon divided by n, or basically this is epsilon times. So with the probability of epsilon, the monkey is jumping to a random node, and with a probability of 1 by n, that random node is going to be this vertex V. And with a probability of 1 minus epsilon, the monkey is not going to randomly jump to a graph, but it's going to follow an outgoing edge from wherever it is currently and then reach the vertex on the other side. Okay, so this is the actual PageRank formula. And what we're going to see is that this particular formula addresses all these problems that we saw with the previous naive PageRank formula. Any questions about this formula itself before we take up some examples?
Yes, sir. Like epsilon by n, sir. Isn't that going to be very, very small, because epsilon itself will be like a number less than 1, and n will run into millions or billions, or I don't know how much. I mean, but so wouldn't that be epsilon by n be very small?
Well, you can ask the same question about the values of the PageRank. If n is in billions, then how large do you think these values of pi's will be? They will also be very small, right?
Yes,
Because
sir.
the sum of all of them have to be equal to 1, and there are n of them, capital N of them. So it's okay for actually the value of epsilon, it is believed that the value of epsilon at the beginning of Google was about 1 by 7. Okay, now of course we don't know what they use. In fact, we don't even know whether, how much PageRank contributes to Google rankings. I mean, maybe it still does, but there could be a number of additional signals that they could have developed over time that would also contribute some kind of authority. But this was the original way in which they did it.
So one more question, sir. So about like time, sir. Like, I mean, if it's over a period of 1 day,
Hmm.
or is it over a period of like many years? Like, wouldn't so how does it how does the formula take it to consideration time, sir?
So obviously, okay, so this monkey analogy was just a conceptual analogy. So obviously in that particular analogy, you are looking at the probability in the very, very long term, over years, or whenever you're like to come up with with a value of the probability that is actually close to the theoretical value, you have to do a large number of trials. So the monkey will have to do a large number of jumps from one vertex to another following both these policies before we end up with the values that we are claiming these nodes will have. But the other way in which you can calculate them is just to treat them as a system of equations and then just solve for the values directly, right? Which is what we were doing here when we were calculating the page rank for these individuals. So we had 4 equations and 4 unknowns, and we are trying to solve those equations, right? So that's what we're going to try to do here also. We're not going to actually carry out this kind of a simulation. We're just going to solve for these equations. And we're going to say that in the long run, on an average, if this is the probability with which the monkey will be in U, then this is going to be the probability with which the monkey is going to be in V. Okay, or if this is the page rank of U, this is going to be the page rank of V. And we're going to see how we start from something very, very simple. Okay, we can start with every node in the graph having a page rank of 1 by n. And then we will take all the page rank values of a particular, of all the nodes, substitute them into the right hand side and calculate the value of the left hand side. So in other words, in step t, the value of the left hand side will depend on the values of the right hand side at step t minus 1. Okay, and we're going to keep doing that. We're going to keep iterating, taking the fresh set of values we get on the left hand side, substituting them into the right hand side and getting another fresh set of values on the left hand side. And we'll keep doing that until we converge, until our values on the left hand side converge to some kind of a stable value. And that convergence is going to happen pretty fast. And that's something we can prove. But I don't think we have time for that today. So since we are running out of time. But any other questions about this formula?